Welcome back. In this tutorial, we will use MATLAB Simulink to implement a proportional integral base feedback controller for thyristor rectifiers to regulate its output voltage. Problem statement. Simulate a single-phase, fully controlled bridge rectifier and regulate its output DC link voltage by implementing a proportional integral base feedback controller. Getting started. Let's begin by launching Simulink and opening the previous example. Create a separate copy of the model for this session. And assign a different name. Select the pulse generator block and press the Delete button on your keyboard to remove it. Bring a subsystem block from the Simulink library. Connect the output of the subsystem block to the gate input of the thyristors, so it can serve as the triggering signal. Next, add two GOTA blocks from the Simulink library. Connect one of the blocks to the source voltage output of the multimeter block. Right-click on the signal line, then select Properties. And assign a proper name to the signal. Double-click the GOTA block to open its parameters window. In the tag field, enter VS to represent the source voltage. Set tag visibility to global, so the signal can be accessed anywhere in the model. Connect the second GOTA block to the DC output voltage signal. Next, give proper name to the signal. Open the GOTA block, type VDC in the tag field, and set visibility to global. To design the LC filter, drag two RLC branch blocks from the library. Connect one RLC branch block in series with a load resistor. Connect the second RLC branch block in parallel with a load resistor. Double-click the series-connected RLC branch and set its element type to Hell from the drop-down menu. Double-click the parallel-connected RLC branch and set its element type to C from the drop-down menu. To save time, we can use ChatGPT to estimate the minimum inductance required for continuous current conduction. For a reference DC voltage of 100 volts and an output DC current of 10 amperes, the calculated minimum inductance is approximately 50 millihenry. A value of 100 millihenry is considered conservative, as it provides stronger current continuity, especially at higher firing angles. Therefore, set the series inductor to 100 millihenry in the LC filter design. Next, ask ChatGPT to calculate the required capacitor value for the LC filter. The tool provided different capacitance values depending on the desired output voltage ripple target. For this design, set the capacitor value to 0.05 farads. Rename the subsystem block. Next, open the subsystem block. Delete the in port and the connection line. Rename the out port as triggering pulse. Add the required blocks from the Simulink library into the subsystem block. From commonly used blocks, insert 3 constant blocks, 2 gain blocks, and 1 saturation block. From signal routing, insert 2 from blocks, and 1 selector block. From math operations, insert 2 subtract blocks. From continuous, insert 1 integrator limited block. Next, go to Specialized Power Systems, and then select Control. Insert 1 PLL block. From Power Electronics Control, insert a Thyristor pulse generator block. Arrange the blocks inside the subsystem for proper connection. Rename the subtract block. We will use this block as comparator to compare the actual DC output voltage with the reference voltage to produce an error signal. Rename this constant block as reference voltage. Connect the reference voltage block to the positive input port of the comparator and set its value to 100 volts. You can find the full course link in the video description. Let's start the process of tuning the PI controller parameters. First, disable the integrator limited block to focus on tuning the proportional term, Kp. The result looks good. Further tuning does not produce significant improvement. You can find the full course link in the video description. Change the reference voltage to 50 volts and run the simulation again. The output settles smoothly near 50 volts, indicating stable PI controller performance. Zoom in on the waveform for closer inspection. The voltage reaches approximately 49.8 volts and gradually approaches the exact reference value of 50 volts, confirming proper tracking. Thank you for being with us. You can find the full course link in the video description.